Good morning, everybody. Today I will continue with rotation of rigid bodies. What we have within this chapter, we will describe the rotation of a rigid body in terms of angular coordinate, angular velocity, and angular acceleration. In addition to that, we will investigate rigid body rotation when the angular acceleration is constant. During the second and third chapters, we have discussed the linear acceleration. When the linear acceleration is constant, we have some equations, okay? Then we will use more or less the same equations for this chapter when the angular acceleration is constant for rigid body rotation. And in the next lecture, we will talk about the kinetic energy of the rotation or rotational kinetic energy. And then we will talk about the moment of inertia about a rotation axis. We will discuss these two important topics in the next lecture. And finally, we will calculate the moment of inertia of bodies with various shapes and different rotation axes. So depending on these two important parameters, shape and rotation axis, we will investigate the moment of inertia of different bodies. So in the next chapter, we will also discuss the dynamics of rotation. So this chapter and next chapter will deal with the rotation. Let me tell you here related to a rigid body. This is very important. So real-world rotations can be very complicated because of stretching and twisting of the rotating body. So let's consider a wheel of a car, okay? During the rotation, the shape of the wheel changes. But within this chapter, we will consider that the shape of the rotating body does not change, okay? Then this is called as rigid body. Okay, if you hear or if you read rigid body, it means that its shape does not change during rotation. Okay, don't forget this term. And within this chapter, we will always consider that we are dealing with rotation of rigid bodies. Let me start with the angular coordinate. Remember from the previous lectures, we have x, y, z coordinates and also position vector. Okay, you remember all these things, x, y, z, and r. So in order to define the position of the object in an axis, in a plane, or in three-dimensional system, so we use these coordinates. But in case of rotation, we will use another coordinate, theta. Okay, instead of x, y, z or r, we will use theta. So here on the right side, you see a car's speedometer needle. Okay, this is the needle of a speedometer. What I mean, this is the speedometer of the car. Let's say it is showing 90 kilometers per hour, for example, and here you have 220 kilometers per hour, and this is 0. Okay, this is the speedometer of the car. Here there is a needle within the speedometer, and it rotates about a fixed axis. So this is the rotation axis. Look at the origin. Okay, this is the rotation axis of the speedometer needle. You can also consider analog watches, okay? Here we have x-axis, and here we have y-axis. And this is the speedometer needle. Let's consider that this is the initial angle between the needle and x-axis, which is given with theta. Theta is 0 at the beginning. And after a certain time, the position of the needle is like this. And we have this theta angle between this needle and x-axis. This is given with theta. The angle theta from the positive x-axis specifies the needle's rotational position. Let's choose a position P here, okay, just a point on the needle and call it P. So this is the rotational position, okay, which is given with theta. Axis of rotation passes through origin and points out of page, don't forget. So you can consider, just for clarity, I draw like this. This is the axis of rotation. Okay, now let's define other things. Here we have a speedometer needle, okay, in this graph, and it is from origin to the P position. And the line OP, this OP line, is fixed in the body, okay? It is constant and rotates with it. The angle theta that OP, this line, makes with the positive x-axis is a single angular coordinate. This is angular coordinate. Okay, what I mean, for example, if I ask you what is the position of P, then you can tell me that this is the x position of the point P and this is the y position, and then you can write the position vector in terms of x and y, okay? Instead of defining x and y, we use just theta, okay? Because this theta completely describes the body's rotational position. So what happens? Look at the graph again. Just consider that this is the new position for the needle. Okay. Then this is the new theta angle. Okay. So this theta defines the rotational position and it is called as angular coordinate. Okay. Instead of x coordinate, instead of y coordinate, instead of z coordinate, we call it as angular coordinate for the theta. Now let me continue. Units of angles. You must be very careful when you are dealing with rotation of rigid bodies. So here, what we have, this is the S, arc length, okay? Let's consider that this is the initial position of the particle here during the rotation, and this is the position when the time is 0, let's say, and this S is the displacement of the particle or object here at this point during this rotation, okay? This is given with S. And for certain condition, when this S, this arc length, is equal to R, radius of this circle, this theta is given with 1 radian, okay? And what about the complete revolution? This is the complete revolution, which is given with 360 degrees or 2 pi radians, okay, 2 pi radians. And if S is included within the equations, or if you are using equations derived from this formula, you have to use always radians, not degrees, okay? Be careful with this one. I will come to that point later on. And now let's continue angle in radians. So here we have again S arc length, which is given with radius of the circle times this theta. Okay, and angle theta in radians is the ratio of the arc length S to the radius R. you can also write this expression like this. So this is the displacement of the particle or object along this arc length, okay? You can consider like this. This is the S. And this is the angle which sees this arc length, okay? So we have this relation. S is equal to R times theta. So by using this formula, you can get many equations related to the rotation of rigid bodies, and today we will do that. Please always keep this information in your mind. This S is related to the radius of the circle and also the angle here. Okay, now let's define the angular velocity. Average angular velocity is given with this expression, delta theta over delta t. So what was theta? Remember theta. Theta is angular coordinate. Remember the linear velocity. In case of linear velocity, we are using delta x over delta t, right? The change in the x coordinate. In case of average angular velocity, we are using the change in the theta coordinate or angular coordinate in time interval delta t, okay? So more or less same mechanism. But here we have something else. You must be very careful with this one. The subscript z means that the rotation is about the z-axis, okay? So here, look at the needle again in this graph. Here we have x-axis, here we have y-axis, and this is the origin. And here we have a needle. This is the initial position of the speedometer needle. And let's say this is the final position when the time is t2. And what about the angular velocity? The angular velocity is along this rotational axis, okay? Here, there is a very important information. This is the direction of rotation, counterclockwise, okay? It is also given here, direction of rotation. But what about the direction of the angular velocity? The direction of the angular velocity is determined with the right-hand rule. I will show you in the following transparencies, and it will be along this rotational axis. Okay, don't forget this one. So let me go back to the definition of angular velocity. Here we have angular coordinate theta 1. Here we have angular coordinate theta 2. Yes. And then the change in the angular coordinate delta theta is given with theta 2 minus theta 1, and put them here. And this is the initial time t1. This is the final time t2. Put them here in the delta t. Then you can calculate average angular velocity. So now let me calculate instantaneous angular velocity. You already know that we have done this one for several times for different definitions in linear motion. Here, again, the instantaneous velocity is given with the limit delta t goes to 0, okay, for very short moment, delta theta over delta t. Then it can be written with d theta over dt, time derivative of theta, okay, which is the instantaneous rate of change of body's angular coordinate. So this instantaneous angular velocity, also called as just angular velocity, okay? And here again we have Z, you see omega Z. The name of this symbol is omega, Greek letter, and this is Z. This Z, subscript Z, is showing us the rotation axis. Okay, I will talk about this. And what about the sign of this angular velocity? It can be positive, it can be negative, okay? Depending on the direction of the rotation, we will also talk about this. So now, let's talk about the positive and negative angular velocity. In order to determine the direction or sign of the angular velocity, you have to know the direction of the rotation. If the rotation is counterclockwise, I mean this one on the left side, this is the counterclockwise rotation, then what do you see here? So this is the x coordinate, okay? And this is the initial theta, theta 1, and this is the final theta, theta 2. Okay, this is the delta theta change in the theta coordinate. What do you see? The theta increases, okay? If theta increases, angular velocity is positive. So delta theta is positive, then angular velocity is positive. If the rotation is clockwise, like this, which is shown here on the right side, okay, this is the clockwise rotation. What happens here? This is the, let me show with another color now. This is the theta 1, and this is the theta 2 now, and delta theta is negative, okay? Delta theta decreases. Then velocity is negative, okay? Delta theta is negative, then angular velocity is also negative. So this is the sign of the angular velocity. And the axis of rotation passes through the origin and points out of page. Don't forget this one. And let me continue with this example, example 9.1. Up to now, do you have any question? Okay, then let me continue with this very easy example. Example 9.1, calculating angular velocity. The angular position theta of a 0.36 meter diameter flywheel is given with this expression. Theta is given with 2 radian per cubic second times the power 3 of time. Then the question A, find theta in radians and in degrees when the time is 2 seconds and when the time is 5 seconds. Okay, we will find the theta. Theta is already given here, and we will put this times here and then calculate this theta in terms of radians and also in degrees. So second question, find the distance that a particle on the flywheel rim moves. Here there is an important word, rim. Let me clean this part and you can better see it. Don't forget this word, rim. I can draw it like this. Let's consider this is a wheel, okay? Rim is somewhere here, okay? Find the distance that a particle on the flywheel rim moves from T1 to T2. We will find the distance of a particle on the flywheel rim. So we will calculate this one. I will go into detail. In question C, find the average angular velocity in radian per second and also in revolution per minute over that time interval between T2 and T1. And the last question, find the instantaneous angular velocities at T1 and at T2. Okay, now here, let's start with the question, first question, theta, when the time is T1 and when the time is T2. What is theta 1? Just put here instead of T 2 seconds, and then we have 16 radian. This is the theta 1. And what about in degrees? In order to calculate this radian or convert this radian to the degrees, you can use this expression. 2p radian is equal to 360 degrees. Just put it there, then you can calculate this theta 1 with this 920 degrees. And for the theta 2, just put here 5 seconds, which is given within the question here on the left side. And then you can calculate 250 radian. So finally, you can also convert this radian to the degrees. This is 14,000 degrees. Okay, after 5 seconds, you can imagine how this flywheel is rotating very fast. So now, what about B? Find the distance that a particle on the flywheel rim moves from T1 to T2. Let's consider this is a circular flywheel, and here we have a particle. This is the position of the particle when the time is T1, and this is the position of the particle when the time is T2. So what is the distance between P1 and P2? This is given with S, okay? This arc length S. And S is given with this expression, R times delta theta. And delta theta is given because we have already calculated T1 and T2, okay? Just put them here, then you can calculate 42 meter, okay? R is already given within the question. R is the radius, and where is it? Diameter is given, and then you can calculate the radius from this information, which is 0.18 meter. And here there is an important information. Okay, look at this one. Here, what about S? S is in meter. What about radius? Radius is also meter. Okay, meter and meter. In order to get unit consistency, this delta t or theta must be unitless. Okay, so we can write the theta in radians, we can write the theta in degrees, but it is dimensionless number. Okay, so we can drop radians from the unit for S because theta is a dimensionless number, like our S is measured in meters. So I have already explained, I will not go into detail. Then let me continue with the part C, average angular velocity. Average angular velocity is given with delta theta over delta t. So delta theta is already calculated here, put it there. Delta t is given. Then average angular velocity is given with 78 radian per second. And something else, you have to find this average angular velocity in revolution per minute also. Revolution per minute. So we have found it in radian per second. In order to convert this one to the revolution per minute, what you have to do, here we have a second, you have to convert this second to the minute. Here we have a radian, you have to convert this radian to revolution. How to do that? One revolution is 2p radian, right? We are talking about one revolution, okay, which is given with 2p radian. and 1 second is given with 1 minute is given with 60 seconds, and then you can write this one in revolution per minute. And what about the D? Find the instantaneous angular velocities when the time is 2 seconds, when the time is 5 seconds. What about the instantaneous angular velocity, which is given with the time derivative of theta? Theta is given in the question, okay? Take the time derivative of this one, then you can calculate the instantaneous angular velocity. This is the instantaneous angular velocity. So here we have t. Instead of t, just use 2 seconds and 5 seconds. Then you can calculate instantaneous angular velocity or angular velocity when the time is t1 and when the time is t2. Any question related to this example? Let me continue with the direction of the angular velocity. Don't confuse with the direction of linear velocity and angular velocity in rotational motion. So here, have to find the direction of the angular velocity. Let's consider that this object is rotating around this axis, okay? And this is counterclockwise rotation. This is the direction of the rotation. This one, direction of rotation. Okay, not the direction of the velocity. This is direction of the rotation. Okay, if you have such direction of rotation, then by using the right hand rule, your 4 fingers will show the direction of the rotation, and the thumb here will show the direction of the angular velocity. Okay, so the angular velocity is always along the rotation axis, okay, in this perfect condition. If the object is rotating clockwise, so then by applying right hand rule, the direction of the angular velocity is opposite to the first case. In many examples, many problems, students usually confuse the direction of the linear velocity and direction of angular velocity, and also this information. Look at this one. This arrow is not the direction of the angular velocity. This arrow is showing us the direction of rotation, and the direction of angular velocity is about the rotational axis. Now, let me continue. If we are talking about counterclockwise rotation like this, the omega points, the angular velocity points in the positive z direction, then we have positive angular velocity, okay, in counterclockwise motion. In clockwise motion, omega is negative, okay, because omega points in the negative z direction. This is the negative z. So, another important information, caution from the book. Let me also read this part for you. The angular velocity vector is perpendicular to the plane of rotation, not in it. So remember the linear motion. Let's consider we have a road and there is a car here. It is moving with some certain velocity and it has certain displacement delta x, okay? So what do you see here, that this velocity is this plane, okay? Plane of motion. But in case of rotation, let's consider here we have an object and this is the direction of the rotation, okay? And this velocity is perpendicular to the plane of rotation. This is the plane of rotation, XY plane. This object is rotating in XY plane. This is the direction of the rotation, but the angular velocity is perpendicular to the rotational plane or rotation plane, okay? So here, again, caution, it is a common error to think that an object's angular velocity vector, omega, points in the direction in which some particular part of the object is moving, okay? This is not correct. Another error is to think that omega vector is a curved vector that points around the rotation axis in the direction of rotation. So this is not the omega vector, okay? This is not the omega vector. Omega vector is this one. So now let me continue with the angular acceleration. Look at the term. Now we are talking about the acceleration. Up to now we have discussed the angular velocity and angular coordinate. Now we will continue with the angular acceleration. Look at this one. What do you see here? This is the direction of the rotation, counterclockwise, okay? And here you see omega 1z. What is this? Here we have discussed the caution, okay? What we have discussed here that omega is not a curved vector, okay? If this wheel is rotating like this counterclockwise, then we have angular velocity vector in this direction, right? But why here we have omega 1z? This is just showing us the magnitude of the omega, okay? Not the direction of the angular velocity vector. This is the direction of rotation, this curved arrow, okay? This curved vector is the direction of rotation, but the direction of the angular velocity is along the rotation axis. Don't forget. Then let me continue after cleaning this part. The average angular acceleration is given with delta omega z over delta t, the change in the angular velocity over time interval, okay? Then the final angular velocity of the object minus initial angular velocity of the object and the time interval. Then you can calculate the average angular acceleration. Look at the symbol of the angular acceleration. This is alpha, okay? So let me remind you linear motion. In linear motion, we have used x, y, z, and r in order to show or describe the position of the object. And we have used v symbol in order to describe the velocity of the object. And we have used this a symbol in order to describe the acceleration of the object. In case of rotation, we are using theta in order to determine the position of the object during rotation, and we are using this omega in order to describe the angular velocity, and we are using alpha, okay? It is also vector, okay, which is showing the angular acceleration, and its magnitude is given with delta omega z over delta t. Since it is vector, it is also along the rotation axis. Okay, I will come to that point, the direction of the angular acceleration. And instantaneous angular acceleration is given with this expression. this one, you can get alpha z. This is the average. This is the instantaneous one. Limit delta t approaches 0, delta omega z over delta t, then it can be written with this form. Okay, this is the instantaneous angular acceleration. So now let me also show you this information. We can also express the angular acceleration in this form. Look at this one. This is the instantaneous angular acceleration. Instead of omega z, we can use this one, right? Then put this one into this angular acceleration. Then we will have this expression for the angular acceleration. Remember the definition of the linear acceleration in chapter 2. In chapter 3, we used this expression, right, for the acceleration. So this is the same. So now let me continue with the direction of the angular acceleration. Angular acceleration is also a vector, and its direction is along the rotation axis. This is the rotation direction of the rotation, and this is the rotation axis. If this is counterclockwise rotation, then this is the direction of the angular velocity. Then if rotation speeding up, okay, if this object rotates faster and faster by time, then we have angular acceleration. If it is speeding up, the direction of the angular velocity and the direction of the angular acceleration are same, like in linear motion, okay? If the rotation is slowing down, then the direction of the angular velocity and the direction of the angular acceleration are opposite to each other. Then let me continue with bio application, a bio example. Rotational motion in bacteria in the lower intestines of humans and other warm-blooded animals. Okay, the name is Escherichia coli bacteria, and these are flagella here. These things like spirals, okay, flagella. So the bacteria swim by rotating their long corkscrew-shaped flagella, which act like the blades of a propeller. They have flagella, okay, and their shape is given with this expression, corkscrew. Each flagellum is rotated at angular speeds from 200 to 1000 revolution per minute, okay? It is amazing, huge, about 20 to 100 radian per second, and can vary its speed to give the flagellum an angular acceleration. So they can produce angular acceleration. Then they can travel within the intestines of humans and also other warm-blooded animals. This is the example of rotational motion in bacteria. Let me finish this example. Example 9.2 from the book, Calculating Angular Acceleration. For the flywheel, which we have discussed in example 9.1, find the average angular acceleration. Average angular acceleration between time 2 seconds and 5 seconds, and in part B, find the instantaneous angular accelerations when the time is 2 seconds and 5 seconds. So What about the angular velocity? We have already calculated this angular velocities. Okay, then what about the average angular acceleration, which is given with delta omega over delta t, and omega 2z is known, omega 1z is known, put them here, then delta t is this one, then average angular acceleration can be calculated. So what about the part B, instantaneous angular acceleration? Instantaneous angular acceleration is given with this expression, the time derivative of angular velocity. We have calculated angular velocity as this one. So in this example, remember that the theta is given in terms of or t power 3 as much as I remember. Then we have calculated angular velocity in terms of t square in that example. And now I will use this omega z to calculate the alpha z, angular acceleration. Put this omega z here, which we have calculated in example 9.1, which is given with this expression. Take time derivative of this one. Then finally, we have this expression, angular acceleration, alpha. Then, when the time is 2 seconds, when the time is 5 seconds, just put here 2 and 5, and then you can calculate 24 radian per square second, 60 radian per square second. So here, the angular acceleration is not constant. Okay, but sometimes angular acceleration is constant. Okay, then in case of constant angular acceleration during the rotations, you can use the formulas which are shown here. Okay, look at the equations on the left side. We have already described these equations in chapters 2 and 3. So when the linear acceleration is constant, then we can have these 4 equations. You already know them. Here we have velocity, here we have acceleration, and here we have displacement, okay? But what about the equations when the angular acceleration is constant? Okay, so we have the same, more or less, the equations. Angular acceleration is constant. Then here we have angular velocity, which is given with initial velocity when the time is 0 plus acceleration, angular acceleration times time. So this is the second equation. Final angular position, angular coordinate is given with the initial angular coordinate plus initial angular velocity times t plus 1/2 angular acceleration times t squared. So they are similar. They are similar. So also for the third one and the fourth one, you can see that they are similar to each other. So instead of x or y or z, here we use just theta. Okay, instead of v, we use omega, angular speed, angular velocity. Instead of a, we use alpha in rotational motion. Okay, now within this part, I will extract, I will calculate all these equations. Okay, so here I have told you that you can use these equations for the fixed axis rotation with constant angular acceleration, and within the following transparencies, I will show you how to get these equations, these 4 equations for constant angular acceleration. Let me start with the first one. Let's consider that this is the final angular velocity of a rigid body. And let's consider that this is the initial angular velocity of a rigid body when the time is 0. And this is the delta t, okay? So this is the angular velocity. So then, by using this expression, I can write this final angular velocity with this equation. This is the final angular velocity. This is the initial angular velocity when the time is 0. And this is the angular acceleration of the body, which is constant. And this is the time. So this is the first equation here within this table. And how to get the second one? With constant angular acceleration, the angular velocity changes at a uniform rate. So its average value between 0 and t is the average of initial and final values. We have discussed this information also in the acceleration in linear motion. Okay, you remember this information. This is the average angular velocity, which is given with initial angular velocity when the time is 0 plus final angular velocity over 2, okay? This is the average of initial and final values of angular velocity. So we also know that average angular velocity is given with delta theta over delta t. So this is the angular displacement, delta theta, which is given with theta minus theta 0 when the time is 0. This is the delta t when the initial time is 0, okay? So then just use these two equations that they are equal to each other. Then from these two equations, you can get this expression. This is the total angular displacement theta minus theta 0, okay, when the acceleration, angular acceleration is constant, which is given with 1/2 omega 0z plus omega z times time. This was the fourth one, and now we have two others here. We will calculate them. So here within this equation we have omega z. You see omega z here. And here omega z is given with omega 0z plus alpha z time. Just take this expression and use it there, okay? Then finally, this expression can be written in this form, okay? This is the final angular position of a rigid body. This is the initial angular position of body when the time is 0. This is the angular velocity when the time is 0. This is the time plus 1/2. This is the constant angular acceleration of the body, and this is the t square. So this is the another equation for the constant angular acceleration in rotation. But what we have here, if the time is 0, this term is 0, this term is 0, then the theta angular position is equal to theta 0. If the acceleration is 0, if there is no angular acceleration, then this term is 0. Okay, for certain time, the angular position is given with theta 0 plus initial angular velocity times t. If we have constant angular acceleration for certain time, you have to add this third term here within this equation, then the final angular position is given with this expression. So now let me finish with the last one. How to get this one? We can combine equations 9.7 and 9.11. 9.7, this one here, and 9.11, this one. What we have here, we have in 9.7, we have time, okay? Take time from this expression. If you take time from this expression, we will get omega z minus omega 0 z over alpha z, which is equal to time, right? So just take this time and use this expression instead of time, okay? Then this equation can be written in this form. So what we have here, time-independent equation for the angular velocity and also for the angular acceleration, okay? This is the final angular velocity of a rigid body with constant angular acceleration. This is the initial angular velocity. This is the constant angular acceleration. And this is the displacement, angular displacement, you can say. This is the final angular position. This is the initial angular position. Then we have these four equations for constant angular acceleration in rotational motion. Do you have any question here in this part? Then let me continue with example 9.3 from the book, rotation with constant angular acceleration. You have finished watching a movie on Blu-ray and the disc is slowing to a stop. The disk's angular velocity when the time is 0 is 27.5 radian per second, and its angular acceleration is a constant minus 10 radian per square second. Okay, so what do you see here? The angular velocity, angular acceleration. Angular velocity is positive, angular acceleration is negative. Then it means that the object's rotation is slowing down, okay? Since velocity and acceleration are opposite. A line PQ here, this is the position P, this is the position Q, and here we have a line, okay, on the right side. A line PQ on the disk surface lies along the positive x-axis when the time is 0. What is the disk's angular velocity when the time is 0.3 seconds? And second question, what angle does the line PQ make with the positive x-axis at this time? So angle is asked here. So at the beginning here, angular velocity is asked, and in the second question, theta is asked. This is the direction of the rotation. What about the direction of the velocity, angular velocity? Direction of the angular velocity will be like this. Okay, this is the direction of the angular velocity. So now let me continue. You can use these two equations to calculate these questions for constant angular acceleration. One is angular velocity. Initial angular velocity is known, which is given here. And time is given 0.3 seconds. Okay, put the values here. Don't forget here we have alpha z, which is angular acceleration, which is given with negative number because the Blu-ray is slowing down, okay? Then put minus here. Then finally you can calculate omega z here, which is equal to 24.5 radian per second. And what about theta? This is the theta after certain time. Theta is given with initial theta plus omega 0 z times t plus 1/2 alpha z times t square. So what is the theta 0? Theta 0 is 0, given in the question. Where is it? a line PQ on the disk surface lies along the positive x-axis when the time is 0, okay? This is the initial position or angular position of the PQ line, then it is 0, and omega 0 is also given, time is given, and alpha is given with negative sign, don't forget again, time is given, then you can calculate this one in radian, okay? 7.8 radian, this is the theta. And you can also convert to the revolution, okay? 2p radian is given with 1 revolution. So this is 1 revolution, and it is given with 2p radian. Then this 7.8 radian is equal to 1.24 revolution. What is the meaning of this? This disk has made 1 complete revolution plus an additional 0.24 revolution, that is 360 degrees plus 87 degrees, okay? So the line PQ makes an angle 87 degrees with the positive x-axis. Okay, so you can also calculate this theta by using this expression for the constant acceleration. You know the final angular velocity, you know the initial angular velocity, you know the constant angular acceleration. You don't know the displacement, but you know the theta 0, and this is asked. So just take this one, then you can calculate theta, which is also equal to 7.8 radian. So you can use this one, or you can use this one, then you can calculate the final position of the theta. Any question here? Then this is the last part of this lecture, relating linear and angular kinematics. So in uniform circular motion and also non-uniform circular motion, we have learned linear speed or tangential speed, okay? We have learned tangential acceleration. We have learned radial acceleration or centripetal acceleration, okay? So today we will try to find a relation between linear speed and angular speed. We will try to find linear acceleration and angular acceleration, okay? So with this one, I will finish my lecture. Here you see an object with this shape. This is the shape of the object. And I am choosing a P point here, and this object is rotating around this axis. This is the direction of the rotation, not the direction of the angular velocity. The direction of the angular velocity is this one, okay? This is the direction of the angular velocity. This is the direction of the rotation. So this object is rotating around this axis with some certain angular velocity. And here I have a P point on this object. Here I have another point, Q point, for example. Here I have A point, but I am dealing with P point here. So what about the linear speed of P point? The linear speed of P point is given with the tangential velocity here, okay? V here, right? And what about this V? How to calculate this V in terms of omega? We will do that today. Here we have radius of the circle R. Here we have theta, and here we have S, arc length, okay? The initial position of the P point and the final position of the P point, and S gives us. And we already know that this S is given with R times theta. Theta is this one, R is this one. So now let me continue. We know that this arc length here, this one, is given with R times theta, radius times theta here. And if you take time derivative of this equation, so ds over dt on the left side, R is constant, and on the right side, theta changes by time during rotation, so d theta over dt. So what is this ds over dt? Velocity, okay, this one, linear velocity. And what about the d theta over dt? This is the angular velocity, change in the angular position, angular coordinate, which is the omega, okay? Then I can write this linear speed of P point in terms of angular speed, okay? Then I have this expression. By using this one, I have calculated this one, okay? So now we have relation between linear kinematic and angular kinematic, okay? Let me give you some more information here in this graph. This is the linear speed, which is given in terms of angular speed. So what about the angular speed of object here? So this is our main object. This object is rotating around this axis. It has certain angular speed. Okay. And this is constant, okay? Let's consider this is constant. So what about the angular speed of this point on this object? What about the angular speed of this point on this object? What about the angular speed of this point on this object? Angular speed is constant for each point on this object. But what about the linear speed for this point on this object? What about the linear speed for this point? What do you see here? That linear speed depends on the radius. So for P point, radius is given with R, but for this point, radius is smaller. For this point, radius is smaller, okay? So depending on the position or point on the object, linear speed changes, okay? Don't forget this one. For example, you consider wheel, okay? And here you have position 1, here you have position 2, and let's consider this is the rotation axis, okay? This object is rotating around this axis, let's say. So it has certain, let's say it is the direction of the rotation. Let's say this is the omega z, okay? And what about the V1? What about the V2? Linear speed of 0.1 and linear speed of 0.2. So linear speed of 0.1 is bigger than linear speed of 0.2 due to this relation, okay? So you will have such problems later on. Then let me continue with the acceleration. So we have learned linear acceleration in linear motion, and now we will get a relation between linear acceleration and angular acceleration. How to do that? So look at the graph again here on the right side. This is the direction of the rotation. Don't mix. This is not the direction of the angular speed. Okay, this is just direction of the rotation. Here we put omega just to show the direction of the rotation, but not the direction of the velocity. Direction of the velocity is this one. Okay, direction of angular velocity. Okay, now let's consider that on the right side we have a rigid body whose rotation is speeding up. Okay, then it has non-constant angular speed. Okay, so now let's have a look on the acceleration, linear acceleration of P point. P point has this type of tangential acceleration, right? A tangential, and it has also radial acceleration. Remember the non-uniform circular motion. In non-uniform circular motion, speed is not constant and the particle is slowing down or speeding up. So depending on the speeding up or slowing down, we have direction of acceleration forward or backward. Here, the object is speeding up, okay? Rotation is speeding up. Then we have forward direction of the acceleration of the P point, and this acceleration has tangential component and also radial component, okay? And how to write this tangential component in terms of angular acceleration, how to write this radial component in terms of angular velocity. Now we will do that. So this tangential acceleration increases or decreases this tangential velocity in non-uniform circular motion. If the direction of the velocity and the tangential acceleration are in the same direction, then the particle is speeding up in this direction. If they are opposite, the particle is slowing down, okay? So then the time derivative of this linear velocity or tangential velocity of P point will give us the tangential acceleration. We have done this one in circular motion. So dv over dt is the tangential acceleration. Here we have v. Remember the v, linear velocity is given with r times omega, right? In terms of angular speed, just put this one here. R is constant. If R is constant, take this R out of this derivative, then we have here d omega over dt. What is this? Time derivative of angular velocity will give us the alpha angular acceleration. Then A tangential is given with R times alpha. Okay, here A tangential is given with R times alpha. This is the linear acceleration, tangential acceleration, which is given radius of the circle times angular acceleration of the object or rotation. And what about radial acceleration? In linear motion, in circular motion, radial acceleration is given with v squared over r. Instead of v here, just use again this expression, put it there. Then we will have omega square r square here. Then here another r we have. Then this r will cancel, the r will come from this expression. Then finally we have a radial is equal to omega squared times r. We have tangential acceleration and radial acceleration in terms of angular acceleration and angular velocity. Any question here in this part? Then again, let me remind you that always use radians when you are relating linear and angular quantities. So what I have done here we have a tangential. At the beginning, we have written this one in terms of linear velocity, tangential velocity, and we have converted it to the angular acceleration. Here again, we have linear, a radial acceleration. At the beginning, we have described this one with the linear speed, v square, and here we have angular speed, okay? So what about this angular speed? What about this angular acceleration? Both angular speed and angular acceleration are described with theta, right? This theta. What is theta? Angular coordinate. And what about theta? This theta is given with S over R, right? Or S is given with R times theta. So since this theta is given in radian, this must be in radian, this must be in radian, and you must be very careful during conversion between this A tangential, A radial, and also this alpha. So here, this is the importance of using radians as r theta. So let's say this is the theta is equal to 60 degrees. And if it is given with 60 degrees in the question, you have to convert it to the radians, because all these equations are valid for the radian, don't forget, okay? So now let me continue with two examples and then I will finish my lecture. This is example 9.4, drawing a discus, this one, discus. An athlete whirls a discus in a circle of radius 80 centimeter. At a certain instant, the athlete is rotating at 10 radian per second, and the angular speed is increasing at 50 radian per square second. This is angular speed, and this is the angular acceleration, radian per square second. For this instant, find the tangential and centripetal components of the acceleration of the discus and the magnitude of the acceleration. So tangential acceleration is asked, radial acceleration is asked, and also magnitude of the acceleration is asked. Now look at the question. Let's consider that this is the rotation axis, okay? And this disk is rotating along this circular path. Okay, so it is speeding up. So then there is a tangential acceleration. It is circular motion. So we have here a radial, and here we have acceleration of the discus. Okay, so then if you know the A tangential, if you know the A radial, then you can calculate the magnitude of A by using this expression. Okay, how to calculate A tangential, how to calculate A radial. A tangential is given with R times alpha. R is given radius 80 centimeter, put it there. Alpha is the angular acceleration, which is given 50 radian per square second. Put it there, then you can calculate it 40 meter per square second. A radial, omega squared times r. Omega is the angular speed. Angular speed is given 10 radian per second. Okay, then put it there, radius is given, put it there, then a radial is calculated. Take this a tangential and a radial, put this in this equation, then you can calculate magnitude of this a acceleration of the discus. Any question here within this example? Okay, then let me finish the lecture with this last example, example 9.5, designing a propeller. Let's consider you are an engineer in TAI, TUSAŞ, or in another plane company or in motor company, for example, propellers for ships, okay? Then you are designing a propeller. You are designing an airplane propeller that is to turn at 2,400 RPM, revolution per minute or rotation per minute, okay, RPM. The forward airspeed of the plane is to be 75 meters per second. This is the forward speed of plane, and the speed of the propeller tips through the air must not exceed 270 meters per second. What is the propeller tip? This is the propeller tip. Okay. The speed of the propeller tips through the air must not exceed 270 meters per second. This is about 80% of the speed of sound in air. If the propeller tips moved faster, they would produce a lot of noise. So the motor, the propeller, the plane must be very silent, okay, during its flight. So then this is the maximum speed, propeller tips speed. What is the maximum possible propeller radius? The radius of the propeller is asked. And with this radius, what is the acceleration of the propeller tip? Acceleration of the propeller tip. So this is the sketch of the example. This is the plane, this is the propeller, this is the radius, and this is the tangential velocity, which is given r times omega. This is the forward speed of the airplane, which is given with 75 meters per second in the question. And this is the rotation of the propeller. It has 2,400 revolutions per minute. So what is the question? Maximum possible propeller radius and acceleration of the propeller tip. So R and A are asked. So angular speed is given 2,400 RPM, rotation per minute or revolution per minute. So instead of revolution per minute, we have to use radian per second, okay? Here we have revolution. We have to use radian because these equations are valid when the theta is radian. So then you have to convert this rotation per minute to the radian per minute or radian per second, okay? So then this is the revolution per minute. Then 1 revolution is equal to 2 pi radian, and 1 minute is 60 seconds. Then I have converted this one to the radian per second. And what about the velocity of the tip? Look at this one. This is the tangential velocity of the tip, propeller's tip, okay? And there is also velocity of the airplane in this direction, or in this figure in this direction, velocity of airplane. So what about the velocity of the tip? So velocity of the tip is given with tangential velocity of the tip and also the velocity of the plane. So if you apply this rule, then I can calculate. Look at this one here. V tip square is equal to V plane square plus V tangential square. This one. V tip square is equal to V plane square plus V tangential square. Okay, so then what we have here, we know the V tip, which is given in the question. We know the plane speed, it is also given, and we know the omega, it is given. R is not given, then I can calculate R by using this expression. So R is 1.03 meter. So with this radius, what is the acceleration of the propeller's tip? The centripetal acceleration of the particle is given with A radial omega square times R. Instead of omega, just use angular velocity, which is given. Where is it? Here, in terms of radian per second. In the question, it is given with revolution per minute, and we have converted to the radian per second. Just use it. R is calculated, just put it there. So finally, we can calculate radial acceleration, which is given with 6.5 times 10 to 4 meter per square second. And you can also write this one in G. 1G is equal to 9.8 meter per square second. Then this is equal to 6,600 G. This is the radial acceleration of the propeller. Do you have any question with this example? Okay. So next lecture, I will continue with rotational kinetic energy. You have already learned the kinetic energy in linear motion. Okay, we have discussed the kinetic energy, potential energy, mechanical energy in the previous lectures, and in the next lecture, we will discuss the kinetic energy of the rotating bodies. With this one, I finish my lecture. Take care of yourself. See you on Thursday. Bye-bye.